Welcome to this explainer. Today, we're diving straight into the hidden math of global shipping and what really happens when massive cargo ships mix different fuel oils in their tanks. It might sound like a super niche engineering problem, but it's actually a fascinating look at the daily, high-stakes math that keeps global trade moving across our oceans. We're going to break down exactly how these calculations work, step by step.
Imagine you're at the pump, and you accidentally mix premium with regular or worse, diesel with gas. Total panic, right? You'd be wondering if your engine is about to sputter out and die. And for a car, yeah, that's generally a massive mistake. But on a huge cargo ship, mixing fuels isn't an accident. It's just a regular Tuesday. But because marine engines are incredibly sensitive and the fuels are so ridiculously dense, this routine mixing requires exact engineering calculations to keep those massive engines running safely. They can't just guess what happens next, they have to know for sure.
Here's how we're going to break this down today. We'll hit the core fuel mixing problem, define specific gravity, bust a common math myth, reveal the correct formula, and finally, look at why getting all this right actually matters out on the water.
All right, Section 1, the fuel mixing problem. Let's look at why ships even need to mix fuels in the first place. Unlike your car, where you usually just run the tank and you're empty and fill it up with a single type of gas, it's perfectly normal for a ship to mix fuels constantly. They might be bunkering, which is just the maritime term for fueling up, and loading new fuel into a tank that's already partially full. Or, they might be transferring fuel internally from one tank to another just to keep the ship balanced. Oftentimes, they're simply mixing leftovers from a previous voyage with a fresh batch. This means engineers are constantly dealing with a newly blended cocktail of fuels in their tanks, and they need to know exactly what's in it.
Moving right along to Section 2, what is specific gravity? Because to mathematically understand what happens to this mixture, we first have to define a crucial metric that ship engineers use every single day.
Specific gravity, or SG, simply tells us how heavy a liquid is compared to water. It's a ratio. We use pure water as our universal baseline, assigning it a strict SG of 1.000. Everything else is just weighed against that baseline to see if it's lighter or heavier than water.
Check out some of these everyday liquids to see what I mean. Standard gasoline has an SG of 0.72, meaning it's quite a bit lighter than water. Diesel comes in at 0.84, but look at marine fuel oil. It sits right up against that 1.00 baseline, ranging from 0.89 to 0.99. This stuff is incredibly thick and heavy. So in practice, an SG of 0.90 just means that 1 liter of that marine fuel weighs exactly 90% of a liter of water. It's a beautifully simple but incredibly powerful way to standardize how we measure liquid density on board.
Okay, Section 3, the common averaging mistake. This is the mathematical trap almost everyone falls into when they first start mixing these heavy marine fuels. It seems so simple, but intuition can be a really dangerous thing in an engine room.
Picture this scenario. You mix 20,000 liters of fuel A, sitting at a 0.89 specific gravity, with 15,000 liters of fuel B, sitting at 0.93. What happens? Human intuition screams at you to just average the two numbers, right? Add 0.89 and 0.93, divide by 2, and bam, 0.91. Looks perfectly reasonable on paper.
Well, actually scratch that, because that simple average is completely wrong. It is only ever correct if both fuel volumes are exactly mathematically equal. But here, they aren't. We've got 20,000 liters of one and 15,000 of the other. That massive 20,000-liter batch has a way bigger physical influence on the final density of the mixture. It literally pulls the final specific gravity closer to its own number. So to get the real answer, we have to use a weighted average instead.
Which brings us to Section 4, the correct SG formula. Let's look at the exact math these maritime engineers rely on to avoid disastrous miscalculations.
Now, don't let the brackets scare you off. This formula is actually quite elegant. You just take the volume of the first fuel, V1, and multiply it by its own specific gravity, SG1. Then you do the exact same thing for the second fuel. You add those two results together to get your total weight equivalent, and then simply divide that chunk by the total combined volume of the tank.
Let's break this down into 4 foolproof steps using our previous example. Step 1. Multiply each individual volume by its specific gravity. Step 2. Add those two results together. Step 3. Figure out your total volume by adding the liters together. And Step 4. Divide the combined results from Step 2 by the total volume from Step 3. Let's plug the numbers in and see it in action.
methodically working through this. In step 1, our 20,000 liters times 0.89 gives us 17,800, and our 15,000 liters times 0.93 gives us 13,950. Moving to step 2, we add those up for a solid 31,750. In step 3, we just add our raw liters together to find our total tank volume of 35,000 liters. And for the grand finale, step 4, divide 31,750 by that 35,000 total. Doing this lands us on our exact reliable answer.
And drum roll, the true specific gravity is 0.907. Remember earlier when our gut told us the simple average was 0.91? Well, 0.907 makes perfect logical sense when you look at it. It's slightly closer to 0.8, right? Why? Because Fuel A had that larger volume of 20,000 liters. Its greater mass literally pulled the final specific gravity down towards its own value.
Finally, Section 5, Why Accurate SG Matters. We've conquered the math, but let's connect these decimals on the page to the spinning purifiers and massive tanks of an actual ship. This isn't just a classroom exercise. This determines how a multi-million-dollar vessel operates.
When you look at these 4 core reasons, the operational impact is huge. Number 1, fuel weight. Ships actually buy their fuel by mass, but the tanks on board can only physically measure volume. If engineers get the SG wrong, they'll completely miscalculate the mass of the fuel they just spent thousands of dollars purchasing. Number 2, without an accurate SG, they'll incorrectly estimate their remaining fuel inventory, which is absolutely terrifying in the middle of the ocean. Number 3, and this is super mechanical, fuel purifiers on ships literally spin the fuel to separate out water, and they rely entirely on exact density settings. If the SG is wrong, the purifier fails and dirty fuel hits the engine. And finally, number 4, it helps them monitor fuel quality.
Honestly, a sudden, unexpected change in your SG calculation could flag a shady supplier, a totally different grade of fuel, or even severe contamination in the tanks. That is exactly why dodging these common math mistakes is absolutely critical for safe operations. You can never rely on simple averaging, you can't forget to add your total volumes, you must never mix up your liters and kilograms, and you always have to double-check your baseline SG. Literally one tiny decimal error can throw a ship's entire fuel management system completely out of whack.
So, I'm going to leave you with this final challenge to test your new engineering chops. Grab a calculator or some scratch paper. If you have a tank containing 18,500 liters at 0.91 SG and you load in an extra 21,500 liters at 0.93 SG, what is the exact specific gravity of the new mixture? Remember to use that weighted average formula we just learned. Taking the time to understand this hidden math really gives you a totally new appreciation for the crazy precision required at sea. I mean, if one small decimal point can compromise a multi-million-dollar cargo ship, what other invisible calculations are quietly keeping our entire global supply chain afloat?